So for our last two sections from Chapter 7, I put together some slides, and I hope I give a good, clear explanation. Please be ready to ask any questions in class on Wednesday. So the physical interpretation of what we've done in this chapter so far has been limited to the process of forming a solution, not the properties of it. What I mean by that is, remember when we talked about the hydration sphere and the fact that the ions sort of orient the water molecules around them? The thermodynamics associated with that was really the formation of the solution. But the properties of the solution with ions dissolved in them centers on a highly regarded theory by Peter Debye and Erich Huckel, the Debye-Huckel theory. So working from simple assumptions, they calculated the potential at each ion caused by the field of the other ions in a so-called ionic atmosphere. This should sound familiar to you, or not so much familiar, but analogous to the hydration sphere we talked about with the water molecules, the solvent molecules. Now this isn't that. We're talking about the anions that are put into solution with the cation. So if you're thinking about sodium chloride, I've got a little sketch here of a sodium cation is in a field of other chloride ions. The scale of this sketch is a bigger volume than we did with the hydration sphere. So these anions in a dilute solution are not really right next to the cation. They're somewhat far away, but they still exert a field. We talked about how the Coulomb's law went as 1 over r squared. So even though the field may be relatively weak, you can see that it's going to have an effect in the right-hand side of my sketch here. So one of the properties of ionic solutions or electrolyte solutions is conductance. And so if you flip on the on switch and the cathode, that's where reduction occurs, essentially a negatively charged electrode, draws this cation toward it, what we're saying is that the chloride ions or the anions are sort of holding it back a little bit. It's slowing down the mobility that you might have predicted just looking at mobility values from earlier in the chapter. So this ionic atmosphere has this effect on the property of conductance. Now I said in the homework I shared with you last time, ionic strength was mentioned. I didn't say at the time that that was developed by G.N. Lewis, the same person, Gilbert Lewis, the same person that invented Lewis dot structures. Ionic strength takes into account the effect that larger charges have greater Coulombic effects. And so you might remember that one of the homeworks used these equations, even though I didn't present this material to you. Now, although the sketch I just put on this slide for you looks pretty easy, the math can be pretty complex. And the reason is because, as I showed here in my cartoon, the cation can be feeling the force of many anions, and they're all going to be at different distances, so it can be kind of some challenging math. That said, the Gibbs energy of each ion can be related to the activity coefficient of that ion. So the activity coefficient, that's the gamma value for a particular ion, but you can't measure a gamma for an individual ion directly. It's convenient to express this and other properties in terms of the mean ionic activity coefficient. I see my mistake here. I can't say a typo, but I forgot to write mean ionic activity coefficient. It's pretty easy to calculate that value with the access to the ionic strength value, which you can get pretty easily from the equation above. This is called the Debye-Huckel limiting law. This version is really pretty good for dilute solutions at room temperature. So there's 2 points about the Debye-Huckel limiting law I want to state. First, in a solution of several electrolytes, so let's say you mix some sodium chloride with some potassium nitrate. Now, all the ions contribute to the ionic strength of the solution, but the Z plus and Z minus refer only to the activity coefficient value for the electrolyte you're calculating. So you could calculate gamma plus minus for sodium chloride, even though there's some potassium and nitrate there. So you really have to be precise about what the gamma plus minus is referring to. So you can use Debye-Huckel, the limiting law, to calculate a gamma plus or gamma minus. those values would relate to the gamma plus minus, which we say can be generated experimentally. So gamma plus minuses can be attached to experimental variables. In order to convert them into individual values, you need this equation 726. So look at this sketch I took from your book. So the Debye-Huckel limiting law holds pretty well for the square root of ionic strengths that are about 0.3 or less. So in the sketch, you see that the the straight lines, the black lines, those are lining up perfectly with the Debye-Huckel limiting law. The experimental values are in the red, and you can see that they deviate once you get to larger concentrations. So that means you're going to need to modify the Debye-Huckel limiting law to reproduce deviations that you see. Now, they get a little philosophical here a little bit, so they're saying the generally good agreement with the early portions of the figure argues strongly for the existence of the idea of an ionic atmosphere. So essentially the cartoon that we had on the previous slide is corroborated by these results. So the theoreticians tell us that the ions actually move in more of a zigzag path in a strong field, jumping from one solvent hole to another, whereupon a new atmosphere forms that applies its drag to the ion. There's a good paragraph in the text that gets into the details of this. They talk about kind of a relaxation time. There is a time that it takes for the ionic atmosphere to form. And the fact that if you ramp up the electrode potential, you could actually have the ion being dragged to the electrode so quickly that the ionic atmosphere doesn't have time to form. And you can see this increased conductance get named this thing called the Wien effect, the Wilhelm Wien effect, is another piece of evidence that ionic atmospheres exist. If you could basically have the electrode so strong that you outrun the ionic atmosphere, that's sort of an indirect piece of evidence that the ionic atmosphere does exist. So the next section talks about how these properties of an electrolyte solution can help you in the lab. And this is called the salting in and the salting out effect. So there's some useful applications of the Debye-Huckel to biochemistry. Now, for example, we'll see that in a mixture of proteins, you could change the conditions of the solvent and achieve a sort of selective precipitation. That's a term that's kind of left over from analytical chemistry, but we can use that here as well. So the temperature of the solvent, the pH, the dielectric constant of the solvent, and the ionic strength all can be altered, and they all will affect the solubility of your solute. So although I frame this in terms of applications to biochemistry, just to understand this, let's look at a simple salt like silver chloride. Now, you know silver chloride is a sparingly soluble salt, but just for the sake of argument, let's say a few of those formula units dissociate into silver ions and chloride ions. Now, we'll define the, quote, apparent solubility product. Now, this is close to what you learned in Gen Chem. In Gen Chem, you did molarities. Here, we're using molalities. And you might recall that molalities and molarities are basically the same when you have dilute concentrations. So KSP is the concentration of the cation times the concentration of the anion. But now we're going to apply what we've learned in this chapter to define a new expression. And the new expression is called the thermodynamic solubility product. So KSP with a naught in the superscript. KSP with the naught, or the thermodynamic solubility product, is going to be the product of the activities of each ion. Not the molalities, but the activities. Remember that the activity can be thought of as the effective concentrations. We have equations for what activities are equivalent to from earlier. They're activity coefficients times molalities. This is all consistent if you want to review back on page 280. So making the substitution, you can see that this thermodynamic solubility product can be viewed as the product of individual activity coefficients times the normal KSP that we learned in the past. What we've learned is that coulombic forces of the ions in solution influence the behavior of solute molecules in solution. Therefore, the effective number of particles is not what you would expect just by knowing the molalities. Recall our discussion of ion pairs, for example. So you don't necessarily have the number of moles of formula units that dissociated being exactly the number of particles that are acting independently in solution. A cation and an anion can be in each other's sphere close enough that they act as a unit, even though they may be separated by one or two solvent molecules. So the KSP naught and the KSP are going to be different values. They're going to be more different from each other the less ideal the solution is, if that makes sense. So the, let's say, more concentrated the solution gets, you'll get more ion pairs, and so the KSP naught will be farther away from the KSP. So applying another principle we learned, that it's impossible to make an experimental measurement that is directly connected to a single ionic value, we're going to apply the mean values that we mentioned so that the individual activity coefficient terms that I had in this equation become converted into a mean ionic activity coefficient. So because this is a one-to-one salt, this is exactly equal to the mean activity coefficient squared, and so I substituted that into the expression from the previous slide, take the log of each side and rearrange. And so you end up getting an expression that is similar to the one that we had for Debye-Huckel. So we had an expression for Debye-Huckel that connected mean activity coefficients with this term here in the limiting law, and now we can equate that to this ratio of equilibrium constants. So for a one-to-one electrolyte like silver chloride, we can say that the molar solubility, the amount of stuff that dissolves, can be tied to the solubility product. So if you think of like an ICE table, you might remember that we didn't use the letter X in the IC table, we used the letter S. And S for a one-to-one salt is exactly equal to the square root of the apparent molar solubility. Extending this definition to our thermodynamic molar solubility, we could just call the square root of KSP naught equal to S naught. And so therefore we're going to make a substitution into the equation I had above, and then extend it out a bit to get the form of a straight line. So hopefully you can see you've got a nice y equals mx plus b form of this work we've done in the slide, and this will end up allowing us to get the thermodynamic solubility by plotting the log of the apparent solubility. That's the number that's actually measured in the lab, the log of the apparent solubility versus the square root of the ionic strength, and you can get this sort of theoretical term, the S naught. Pretty straight. In plain water, it's very easy to get an S value. You could just see how much salt dissolves and then observe when it starts just going to the bottom of the solution. For silver chloride, the molar solubility is 1.3 times 10 to the minus fifth moles per liter. And so let's think about that term in terms of the equation that we just derived. So the sort of solubility version of the Debye-Huckel limiting law. Look carefully at this. This essentially is saying that I could affect the value of that ratio, S over S naught, by playing with the ionic strength. So if I increase the ionic strength, let's say I added a non-reacting salt, like potassium nitrate, that means that the value of capital I will go up. Well, what's going to go up on the opposite side? It's going to be the solubility. Any kind of increase in S naught is going to be viewed as relatively stable, but the S value is going to have to go up. It's the only variable on the left-hand side of the equilibrium sign. So I really should have drawn my arrow going up this way. So that ratio is going to go up. Essentially what you're saying is that if I can increase the ionic strength of this solution by adding an inert salt, I can actually increase the solubility of silver chloride. This is called the salting in effect. So increasing ionic strength increases solubility. Now, we've already seen that in the Debye-Huckel limiting law, how those curves really went far away from the straight lines as the concentration of ions gets larger, you can get an empirical fit to that part of the curve by essentially deriving a new term. So instead of the part that I have above, the Debye-Huckel limiting law, you can fit the curve by including a new constant, K prime. It's a positive constant that's dependent on solvent and the electrolyte. So you might remember that there's sort of an upward deviation from the straight line. It's this empirical term which will do that for you. The negative sign of this high ionic strength contribution is telling you that solubility is dropping at higher ionic strength. Take the time to look back at the Debye-Huckel curve, and you'll see that the sort of attraction or the deviation from the straight lines is sort of turning those lines upwards. This negative sign is telling you that at the high ionic strengths you can have a so-called salting out effect. In short, the process of hydration is the reason. You literally start running out of water molecules that are available to hydrate the new electrolyte. As you're sort of putting in your salt, if there's a lot of ions already in that solution, you literally run out of hydrating water molecules. This salting out effect is particularly noticeable when proteins, who have very, very large surface areas and require lots of water to solubilize. We'll see some examples of that now. So let's combine the two different sort of regions of our Debye-Huckel limiting law into a single equation. So the first equation, remember, this is going to apply to lower values, or this will dominate lower values of the ionic strength. And this part of the equation will dominate with higher values. And you can, again, actually get pretty good results. It's a pretty simple equation. This equation is pretty good over a wide range of ionic strengths. Now, look at the graph I have here. Notice how the presence of various inorganic salts affects the solubility of a big protein, a horse hemoglobin. This protein exhibits salting in at low ionic strengths. So what we're saying here is that you could add some inert salt to your solution and cause more of the hemoglobin to dissolve. Notice the, again, upward slope at these ionic strengths. That's the salting in. But as the ionic strength increases, moving to the right, the curves go through a maximum and eventually the slopes become negative, indicating that the solubility decreases with increasing ionic strength. Basically, this second term is dominating for larger values of I. I have a little question here. What's going on with the sulfates? Well, think about what a sulfate ion looks like. One version of the Lewis dot structure is here, and this is a fairly large ion. In order to solubilize this ion, you need lots of water molecules all the way around in 360 degrees in 3 dimensions. So notice that the sodium sulfate and the ammonium sulfate are good salts for exhibiting this salting out effect. The practical value of this effect can be used to purify mixtures of proteins. I didn't write mixtures here, but I should have used the purified protein mixtures. So this figure shows the range of salting out phenomena for several proteins in the presence of ammonium sulfate. So on the left-hand side here, I don't know how to pronounce these things, but the fibrinogen has a very steep salting out effect. So if I, for whatever reason, had a mixture of fibrinogen, this serum albumin C, and myoglobin, for example, that mixture can be effectively selectively precipitated by just adding inert salts, and the proteins will clump together and separate out of solution, and then you could add some more inert salt and get out the second protein, and add some more inert salt and get out the third. Because, as you know, proteins have different amino acids, different regions of it may be more or less polar. So different proteins are more or less polar. The strength of binding of water molecules to these proteins is going to vary. So I say here again, the precipitation can occur over a small range of ionic strength, and you can get very, very sharp separation. So the idea of electrolytes affecting the properties is going to get wrapped up by affecting the properties that we call colligative properties, the properties that depend on how many particles you have. So I say, for example, here you should expect the freezing point of a 0.01 mol salt solution to be twice the deviation from pure water when compared to, say, a 0.01 mol sucrose solution. Life isn't always that clean. You would think, oh, whatever the number of particles I have is going to be twice for salt. Sometimes we have incomplete dissociation. Then things can get complex. So let's define the Van 't Hoff factor as a ratio between the actual number of particles that are in solution divided by the number of particles that you would predict before dissociation, let's say just by looking at the formula. I noticed that the textbook used the word particles. I really don't think that's the proper word, especially for salts. It would be better to say formula units. So if I dissolve 1 mole of 1-to-1 salt, I would expect 2 moles of particles from 1 mole of formula units. So we had something similar when we were discussing the degree of dissociation back in chapter 6. Anyway, this sort of version of an ICE table defines some terms. So again, alpha is the degree of dissociation, N is the units or formula units of the electrolyte, N times 1 minus alpha is the number of the undissociated units, and N times V times alpha is the units of this ion in solution. So you could have NV plus alpha. That's the number of cation units that you have, and that really should be NV minus times alpha. That's the number of anion units you have. So the Van 't Hoff factor, as we said, is the actual number of particles. That's going to be the number of undissociated units plus the number of ionic units, which is the sum of the cations and the anions. And so if you multiply that out, divide by n, you end up deriving this equation. So it allows you to calculate the degree of dissociation if you know the measured value of that colligative property and what the ideal value is of the number of particles, which is V. So for strong electrolytes, the I value is approximately equal to the number of total ions. It's approximately equal to V. But we'll see in real cases, I may be different than V. The value of I decreases as the molality increases due to formation of ion pairs. Of course, the weed whackers are out in force, being PC, so I just overwrote some narration I did to get you to this last section. But in anyway, I mentioned that I can be something other than an integer when you have ion pairs forming. That's a real challenge. I said in general, formation of ion pairs is most pronounced between highly charged cations and anions and in media of low dielectric constants. For example, evidence has been shown for this, that if you have calcium nitrate, now you might think, oh, that thing's going to be totally soluble. It's going to break up into 3 particles. Well, not so fast. There's actually some evidence to show that this kind of odd cation can form, basically a calcium very close to or forming an ion pair with 1 nitrate. It's really, really difficult to get an accurate equilibrium constant for that experimentally. Maybe that's something you could work on in grad school at some point. But other studies show that odd colligative property results are due to hydration considerations, so even more complicated. Basically, it's repeating that the unavailability of water can be a problem. So deviations can be removed when you can subtract the water molecules that are part of the hydration spheres from the free water molecules that are available when the available solvent is considered in concentration calculations. So remember, like a freezing point determination, the molality is going to be the moles of the solute over the kilograms of solvent. What we're saying here is that if kilograms of solvent, you subtract out the mass of anything due to hydration, you can get a better value for what the M is. But this is tough. So essentially, let's just throw in the letter I, this Van 't Hoff factor, into the colligative property equations that we're familiar with and see what we can get. And we have a very straightforward example here. So if the osmotic pressure of a 0.01 molal solution of calcium chloride is compared to a 0.01 molal solution of sucrose, you can see that you get a different osmotic pressure. So essentially what you do is you take the osmotic pressure equation for the calcium chloride and divide it by the osmotic pressure calculation for the sucrose. Everything cancel, or some things cancel, the temperature, the molarity, the gas constant. All that's left is the difference, the two different colligative properties, which is the osmotic pressure and the values of I. Now you're assuming that the sucrose has a value of 1, so it disappears, and so I calculate the Van't Hoff factor for the calcium chloride is 2.70. It's not 3, it's not 3 particles. On average, you get 2.7 particles. And then we had our equation from earlier that did the degree of dissociation. You plug in the I value and the V value, which is the sum of the two individual V's, you get a value of 0.85. So essentially this is saying that 85% of the calcium chlorides dissociate. There's a few end of chapter problems. If you'd please take a look at those, give them a try before you look at my key. I'll try to post a key a little bit later today. Lot to do to get ready for the next week or so, and I hope this was understandable. Please come to class with any questions.